In this video, we're going to talk about a specific application of stoichiometry, and that is combustion analysis. So what happens in combustion analysis is you take a sample that you've weighed out and you place it inside a furnace. And these are often organic compounds. Uh, Primarily, the elements that make up these compounds are carbon, hydrogen, oxygen. There can be others, but the examples that we'll do, the compounds will only contain carbon, hydrogen, and oxygen, and you burn these compounds. Well, when you burn a hydrocarbon, the only products are carbon dioxide and water. And so the products of that combustion are sent through some filters. One that absorbs water, another one that absorbs carbon dioxide, and then oxygen and any other gases, if there were other elements in our compound, would pass through. Now, these chambers that absorb water and carbon dioxide, they're weighed before the combustion analysis, and then they're weighed after. So the increase in mass is due to the water and the carbon dioxide that are produced in the combustion reaction. And so in this way, we can determine exactly how much water and carbon dioxide were produced by the compound. And then we can use that information along with what we know about stoichiometry and the law of conservation of mass to determine the formula of the compound that we placed in the furnace. So let's talk about the strategy of how we would attack one of these problems. So if our compound only contains carbon, hydrogen, and oxygen, and this is a combustion reaction, then this generic equation will work for all of these compounds that we're burning. So we're burning this carbon, hydrogen, and oxygen compound. The other reactant is oxygen, and the only products are carbon dioxide and water. And so the nice thing about the law of conservation of mass and stoichiometry is that if these are our only products, then all of the carbon in the carbon dioxide that we produced came from our compound. And there's a 1-to-1 ratio between the number of moles of carbon dioxide that we made and the number of moles of carbon dioxide that were in the initial compound. Similarly, all of the hydrogen that was originally in our compound is converted into the water product. And for every mole of water that is produced, that's going to make 2 hydrogen atoms. So all of those hydrogen atoms would have come from our starting material, or all the moles of hydrogen atoms were the number of moles of hydrogen that we started with in our compound. So in this way, we know the number of moles of carbon and the number of moles of hydrogen that were in our original compound. To calculate the amount of oxygen, if we know how many moles of carbon, we know how many moles of hydrogen there were in the compound, we can determine what the mass of those atoms would be. And so we can then subtract that from the original mass of the compound, because all that's left is going to be due to oxygen. And so once we know the mass of oxygen, we can of course convert that to moles. And so now we know the number of moles of carbon, hydrogen, and oxygen. And so now it's just like determining the empirical formula like we've done previously. And of course, if the compound only contains carbon and hydrogen, then we can skip this third step dealing with the oxygen. I'm going to finish this video off with an example that just has carbon and hydrogen, and then I have a separate video with an example where the compound has carbon, hydrogen, and oxygen. All right, so for this example, we're told that polyethylene is a hydrocarbon polymer. It contains only carbon and hydrogen. It's used to produce food storage bags, many other flexible plastic items. And we're doing a combustion analysis on polyethylene that yields this mass of carbon dioxide and this mass of water. We want to know what is the empirical formula. So all of the carbon in our starting material is converted into carbon dioxide. And for every 1 mole of carbon dioxide, that came from 1 mole of carbon atoms in the starting material. So to figure out how many moles of carbon I have in the starting material, I just need to figure out how many moles of carbon dioxide I produced. So I need the molar mass of carbon dioxide. So that's 12.01, 2 times 16, 44.01 grams per mole. So I'll take my mass of carbon dioxide Okay, now we'll do something similar with the water. All of the hydrogen atoms in our starting material ended up in the water, but for every 1 mole of water, I'll have 2 moles of hydrogen atoms. So I'll need to take that into account because I want to know the number of moles of hydrogen atoms. So now I could do this in 2 steps. First, find the moles of water and multiply that by 2, but I'm just going to work that into this problem. So for every 1 mole of water, I'm going to get 2 moles of hydrogen atoms. Remember, the moles of CO2 is the same as the moles of carbon. So essentially, I know that I have C and then H. And so to find the empirical formula, I just need to divide the number of moles of each one by the smallest one. So that's going to be the 8.95 times 10 to the minus 5. So, of course, carbon is going to be 1. And the hydrogen, when I do right, essentially I get 1.997. So that's basically 2. So my empirical formula is C1H2 or CH2.